So in this video, we're going to continue to look at our series shunt configuration, which is relevant for our voltage amplifier. But now we're going to look at our input resistance. So I'm going to define my input resistance as looking in here. So this is our input for our feedback amplifier. And so again, note that I'm considering sort of an ideal case, and I'm saying that let's let this RS associated with our input source be equal to 0. Okay, so let's start by looking at this input side. And again, noting that the RS is equal to 0, we can say that our input voltage VI is equal to our error voltage V epsilon plus our feedback voltage VFB. So we can get that from a KVL loop on that left side. Well, so we can make some substitutions. So our V error voltage will leave for the time being. And we know that our feedback voltage is equal to beta V times V out. Well, we know that our V out, we can substitute for that as well. So we have V epsilon plus beta V, and now our V out, we know, is equal to AV times V epsilon. And again, that's either assuming an open load condition and or that this output resistance for our amplifier is 0. Okay, so now what we can do is we can solve this for V epsilon. So we can say V epsilon is equal to VI divided by 1 plus beta V times AV. Well, why do we want to do that? Well, now that we've done that, what we can do is we can come back and we can look at the current in this resistance Ri. And if we know the current into this sort of node here where we're defining our input resistance and the voltage across this whole thing, which is our Vi, we can define that RIF. So the next step then is to define this current I sub I. So let me come back up here and explicitly label that. So this is our I sub I is equal to V epsilon over Ri. V epsilon divided by Ri. And so using our previous equation, that's just going to be Vi divided by Ri times 1 plus beta V AV. And so like I had said just a second ago, if we're ultimately interested in our input resistance RIF, we know that's going to be equal to our input voltage Vi divided by that input current II. So using this equation above here, we're basically just dividing VI. So let's see if we can make this. Let's copy this and put this here. So basically all we're doing is we're dividing VI by this equation. So we have this, and we're dividing VI. So our two VIs are going to cancel out. And this term that was initially in the denominator is just going to come up to our numerator. And we're going to be left with Ri times 1 plus beta V times AV. So what we see is that our input resistance, RIF, to our feedback amplifier is actually being increased. So we have an increased input resistance. And so that's actually going to be desirable for a voltage amplifier. And so let's look at a very simple voltage divider circuit to consider why. So if we have some input voltage Vi, and we have some input resistance here and some input resistance to our amplifier, so let's say this is Rs and this is RIF, and this is our V in, well, this is the voltage that's going to actually be input to our amplifier. So if this is our V into our amplifier, we want that to be as close as possible to the voltage input here. And so we know that from our voltage divider, this V into our amplifier is going to be equal to V in times RIF divided by RS plus RIF. And so for the case of RIF much bigger than RS, so let's say if we have RIF much bigger than RS, what that means is that this is going to be approximately equal to VI divided by RIF divided by RIF, which is of course equal to VI, which is what we want. So in the next video, we're going to come back and look at our output resistance, and then we're going to move on to our other ideal feedback topologies.